Okay, first of all, let's talk about the test. Overall, I haven't started grading yet. I'm still actually writing up my key, but I did notice not many people even tried number 15, which is really disappointing. This is a really good question. It really uses a lot of algebra, a lot of calculus. It kind of incorporates everything you've ever learned in every math class into one problem. It's a good problem. So I want to extend test 2, give you guys more time to figure out this problem. I'm going to give you some hints here. Again, I haven't completely figured it out myself. I haven't typed in the numbers. But here's the general idea. You have some function whose fourth derivative is equal to a constant. So that means that function must be a fourth degree polynomial. And we know that the fourth derivative is this number. So if we take 4 derivatives here, all these guys will go to 0 when you take 4 derivatives. We just get 4 times 3 times 2 times 1 times C1 must equal W over EI. So we know C1 is W over 24 EI. So there is our general solution, where we have 4 arbitrary constants. Maybe I should have numbered them differently. It looks kind of weird here. It would have been better if my numbers matched my exponents, but whatever, it doesn't matter. They're all arbitrary. Then we apply our boundary value conditions. Remember, the whole point of this problem is this is a beam. Let me stop the share. Oh my God, I wasn't even sharing during that. Okay, once again, let's try this again. We have a fourth degree polynomial that equals a constant. So we write out a fourth degree polynomial, take 4 derivatives, and we end up getting this arbitrary constant in front of x to the 4th must be W over 24 EI. So here's our general solution. We apply these boundary value conditions. Now remember, the idea here is we have this beam that has length L, and there are more advanced versions of this problem where maybe we hang something on the beam, or we got people walking across the beam, and we want to know the deflection. So how much this thing bends, this distance here, we're calling U. So a bend down is a positive U. Well, it can't bend at the ends. The ends are fixed. So U of 0 and U of L must be 0. And we're going to assume that we have continuity here, that the derivatives at the endpoints are also 0. So even when this thing bends, it bends in a way so that it's still level at the endpoints. And it's obvious that from its own weight, it's going to bend the most in the middle. Everything's symmetric here. So our final graph is going to have to look something like this. Here's L. Here's how much we bent versus position, X, where if this is 0 and this is X equals L over here. And our maximum bend will be in the middle, and L over 2. So we apply our boundary value conditions. U of 0 gives us C5 of 0. U prime of 0 gives us C4 must be 0. Work those details out and see. Now we got to find C2 and C3. So we apply these conditions. And you just have to solve the system of equations. I did it by elimination. I hardly ever use elimination, but it did turn out to be a little easier here. And this is the equation you get. That should be, I don't know why I wrote a Y there. It should be U. And let me write that here so it's a little prettier. You should get U equals W over 24 I x to the 4th minus 2L x cubed plus L squared X squared. If you don't get this, then you've done goof somewhere, and a bunch of you did not get that. In fact, I looked through everybody's solutions, and I think only one person had this out of the entire class. So figure it out. Work through the details. Then we want to figure out where the maximum deflection occurs. So we need to set U prime equal to 0. So it's a 4th degree polynomial. The derivative is going to be 3rd degree. You're going to get 3 solutions there. And you're going to get, I'm telling you what answers you'll get. You'll get x equals 0, x equals L, and x equals L over 2. So we have some 4th degree polynomial. We know 4th degree polynomials, our leading coefficients 1, in general look like this. So this guy is 0. We already know U of 0 is 0, and so is U of L. We know that the peak here is going to occur at L over 2. So our graph is going to look like this, just in general. That's the entire function. Here's L over 2. It's a 4th degree polynomial with roots and critical points at 0 and L, and another critical point at L over 2. And it's symmetric about L over 2. But of course, our restriction was X must be between 0 and L. So we don't need all of this. We can erase all this stuff. All right, then we just plug in our values. We just Google all those values. I think I even gave you some of the numbers to use to figure out, really our ultimate goal is figure out this number right here. What is that maximum deflection? And keep in mind, if you're getting something like 18 meters, you've probably goofed. This is, what is it, an aluminum beam? Aluminum's pretty strong. It's not going to bend that much. No matter how long this thing is, that bend is not going to be very much. So I would expect something on the order of millimeters. Don't quote me on this, but I think the right answer might be like 0.79 millimeters. But I haven't typed in the numbers myself to check that. And it's been a year since I've done this problem. Okay, let's do Laplace transforms now. So we have our Laplace transform table. That looks like this. Going forward is pretty easy. Like, say, for example, we wanted the Laplace transform of some polynomial, t to the n. Then we would just use this. So the Laplace transform of t to the n is n factorial over s to the next exponent, n plus 1. So, for example, the Laplace transform of t to the 7th would be 7 factorial, whatever that is, figure it out, over s to the 8th. That's pretty simple. What about going backwards? There's an old math joke. It's a terrible joke, and I've probably told it to you guys before, but I'm going to tell it again. You've got 3 pots, and you've got a flower. And right now, the flower is in the middle pot. You ask a physicist, a mathematician, and an engineer, how do you get the flower from this pot to this pot? Everybody agrees you go to the right 1 pot. Everybody agrees on the solution. Move the flower 1 pot to the right. Now you hand all 3 a different problem. I've got the flower over here and I need to move it over here. The physicist and the engineer both say move it 2 pots. The mathematician says no, move the flower over 1 pot. Why? Because now we've turned it into a problem we've already solved. It's a terrible joke. It's not very funny. But that is the key to most of DE. When somebody hands you a problem you don't immediately know the answer to, turn it into something that looks familiar. So if I wanted the inverse Laplace transform of 1 over s to the 9th, I'm going to use this formula that the Laplace transform of t to the n is n factorial over s to the n plus 1. I'm going to make this look like this. So I'm going to think, oh, well, that's n plus 1, so n here must be 8. So in order to fit this pattern, I want to write this 8 plus 1. I need an 8 factorial here that I don't have. Well, the way to get it there is multiply and divide it. So I really want the inverse Laplace transform of this. Inverse Laplace transforms are linear operators, meaning we can pull constants out. So this is 1 over 8 factorial, the inverse transform of this. Now we fit the pattern. It looks like that. This is t to the n. So 1 over 8 factorial t to the 8. It's a lot like when you're integrating versus taking the derivative. You have to, like with power rule, you bring the power down, but when you integrate, you divide by the power, you go backwards. Same kind of idea. Honestly, for the same reasons. Okay, that one was easy. I'm sure you guys could have figured that one out. But what if we had a harder one? What if we wanted, say, the inverse Laplace transform of 5 over s squared plus 9? Well, we look at our table and find the closest we can find to that. So that looks like this one. I've got an s squared plus something, and then just a number on top, no s on top. Okay, but in order to match this, the square root of what's here must be exactly the same as what's here. So I've got a 9 down here. My k is 3. I need to have a 3 on top. So I'm going to put a 3 on top. So I'm using this formula. Equals, what was that? K over s squared plus k squared. I want to match this formula. So my k here is 3, and that's 3 squared. So I'm going to pull that 5 out. I need a 3 on top, so I'm going to put my 3 on top, and at the same time put 1 on the bottom, so I'm not making stuff up. This is what I want the inverse Laplace transform of. That is sine of 3t. And then I've got this 5/3 hanging out front. Okay, pretty easy still so far. What if I want the inverse Laplace transform of 3s plus 2 over s squared plus 25. By the way, before I forget, if you ever find yourself trying to use this formula here or this formula here, just go through the trouble of doing the partial fraction decomposition. It's more trouble than it's worth. Don't try to use this formula or this formula. Just do the partial fractions and separate it into 2 terms. It's really not that bad. However, the one we're working on, there's no formula that matches that. Don't try to get fancy and try to match up with these. It's not going to work out. We want to use these guys by separating this out. So I'm going to split this up. The s over s squared plus 25 will be a cosine. The 2 over will be a sine. So split this up. I'm going to pull that 3 out. S over s squared plus 25. That's going to be a cosine plus 2. Now to use that sine formula, I need to have a 5 up here. In order to get that 5, I need a 1/5 in there. This is cosine. Let's write this if we want the inverse transform. The inverse transform of that is sine, or is cosine. The inverse transform of this is sine. So we get 3 cos of 5x. Sometimes we call it, when we were doing this last week, I had t on this side, s on this side. This particular chart I'm showing you uses x and s. That's irrelevant. Don't stress too much about that. Whether we call our regular domain t or x doesn't really matter. So since I've already started writing x, I'm going to continue with x. And this is sine of 5x. Okay, now what if we have something, make it a little more challenging. What if we had, we want the inverse Laplace transform of 3 over s minus 2 squared plus 16. Okay, so that matches something in our chart pretty well. That looks like this one. So that's an e to the at times sine of kt. So k here will be 4, or will be 4. So really not much we have to do here. We got to put in a 4 on top and bring it out, bring the 3 out. So this will be the inverse Laplace transform. I can bring my 3/4 out, put in a 4, s minus 2 squared plus 4 squared. This was e to the a t. A is whatever is after the minus, so e to the 2t sine of k. K was this guy here, also there. Oh, if I'm using, got to be consistent. I'm either using x's or t's. All right, what if something doesn't quite fit this format, but we need to make it fit that format? So here are the hard ones. These are the ones that tend to cause the most trouble. What if I want the inverse Laplace transform of 2 over s squared plus 8x, 8s, minus 1? Okay, this does not fit the format of anything in that table. So what I have to do is make this look like the previous problem by completing the square. In the denominator. So I'm going to rewrite this guy here as s squared plus 8s plus 16, half of 8 squared minus 16 minus 1. So use the first 2 guys to complete the square by taking half the middle number, squaring it, adding it, and subtracting it out. So that will be s plus 4 squared And then I got a minus 17. So I'm going to write that as minus the square root of 17 squared. Now I got to look at my chart. That looks like this formula. But I need my k on top. My k was square root of 17, so I need to put that in and take it out. So I'm going to put in a square root of 17 and divide by it. And then I fit my formula. Pull the 2 out and so forth. Okay, so sometimes you got to play around. Sometimes you got to split stuff up and have a sine term and a cosine term. Anytime you've got, say, a linear factor on top, if we wanted the Laplace transform, inverse Laplace transform of, I don't know, 5s plus 7 over, and then we've got some quadratic down here, plus 10s plus 12. Then you're going to complete the square in the bottom, split this up into 2 separate fractions. The s over stuff is going to give you some kind of cosine, maybe with an exponential. The constant over this quadratic will give you some kind of sine, maybe with an extra exponential. Okay, let's actually solve some DEs using Laplace transforms. So let's do the one from the test. The initial value problem we had. This one here, this shouldn't be too bad. So that's y double prime plus 4y equals 4, subject to y of 0 equals 1, y prime of 0 also equals 1. All right, so we're going to take the Laplace transform of everything. So I'm going to write out a bunch of details here. Laplace transform of y double prime plus the Laplace transform of y should equal Laplace transform of 4. The Laplace transform of y double prime is s squared capital Y minus s y of 0 minus y prime of 0. Laplace transform of y is s capital Y minus y of 0. Laplace transform of 4. So we have to look at our chart. The Laplace transform of a constant of 1 is 1 over s. So don't think too much about the 4. That's really 4 times the Laplace transform of 1. Laplace transform of 1 is 1 over s, so 4 over s. Okay, our ultimate goal here is to solve for little y. So we collect all of our big y's together. I've got s squared plus s times y. That will equal 4 over s plus s, because y of 0 was 1, plus 2, because both of those were 1. Solve this for capital Y. So we get 4 over s times s squared plus s over s squared plus s plus 2 over s squared plus s. Okay, I think this is going to be better if we just use partial fractions. Let's combine all this together into one single problem. First of all, I could factor an s out of here. So my LCD is going to be s squared times s plus 1. So this guy has everything he needs. This one needs another s, so he'll be s squared, s plus 1. And this guy needs another s, so 2s, s, s plus 1. So capital Y will be s squared plus 2s plus 4 over s squared times s plus 1. Okay, now we want to do partial fraction decomposition. Nothing in our, if something in the table matched this, we'd be done. We just use the inverse table, we'd be done, we just write it up. But nothing in the table quite matches this. So we're going to have to use partial fraction decomposition to break this up into two separate pieces, something over s squared and something over s plus 1. And I'm looking at this going, there's no way that this is going to turn out to be the right answer because I'm not going to get a sign out of this. So I realized something went wrong, and I realized I forgot about this 4 up here. Somehow that 4 got left out. So we gotta go back a little bit. So right here, we should have a 4 times Laplace transform of y. All right, Laplace transform of y double prime was s squared capital Y minus s times y of 0 minus y prime of 0 plus 4 times all this stuff, sy capital Y minus y of 0. And that should be, again, over here, 4 over s. All right, so what do we got here? I've got s squared plus 4s times y. Those are all my y's. That's a minus s, minus 1, minus another one, so minus, no, that's minus 4 there. So on the other side, when I move everything over, I have a 4 over s plus 4 plus s. So y will be 4 over s squared plus 4s plus 4 plus s over s squared plus 4s. Okay, we want to get a common denominator. We're going to have to do partial fraction decomposition. So again, I can pull this s out here, call this 4 over s squared times s plus 4. Pull an s out. I need to multiply top and bottom by s here to make this an s squared. So this will be s squared plus 4s. So now we can combine together. This is s squared plus 4s plus 4 over s squared, s plus 4. That factors on top there, by the way. That is s plus 2 squared. This was still not working out, and I realized I've been stupid this entire time. I thought about just erasing this whole video and starting over, but we had all that good stuff at the beginning, and I don't want to do that. That's not a y prime there. That's Laplace transform of y. That's not y prime. All that stuff I had in there was wrong. This has not been a good video. Laplace transform of y double prime is s squared capital Y minus s times y of 0 minus y prime of 0. That part was right. That's just the Laplace transform of y, which is just capital Y. So plus 4 capital Y equals 4 over s. Find our y's, get them together. This problem is so much simpler than I was making it. S squared plus 4 times capital Y will equal 4 over s plus an s from right there, that's 1 times s plus a 1. Pull everything over, y then, just solve that for y. 4 over s times s squared plus 4 plus s over s squared plus 4 plus 1 over s squared plus 4. Okay, now we want to do partial fractions on this one. This one I can do. That one's not bad. That's pretty easy. That one I could do. That's just a sine of 2x right there. That's a cosine of 2x. But I need to split this one up. I could combine all these into one thing and then do the partial fraction decomposition. But I find it easier just to deal with each piece. If you can already do one, why squish it together with other ones that are difficult? This one we need to split up because I don't have something that looks like this in my table. So I want to split 4 over s times s squared plus 4 into a over s plus b over s squared plus 4. So we get 4 is a times s squared plus 4 plus b. Oh, wait, no, that's not going to work. We need, this is an irreducible quadratic. This one has to be linear. So I need a bx plus c times an s. And I'm trying to find a, b, and c. So I like to just match up. This should be an s. I like to match up my front guys. So I'm going to have an as squared and a bs squared. Over here on this side, I don't have any s squared, so those must equal 0. So a is negative b. My constant term, a times 4, must equal 4. So a must equal 1, meaning b equals negative 1. And then my s term, I'm going to have a c times s must equal 0, because there's no s term over here, so c equals 0. So what we get, if my partial fraction was correct, is 1 over s minus 1 times s, so minus s over s squared plus 4. Okay, so that replaces this. So we get y equals, hey, look, those two cancel. Remember, there was no cosine in the answer. 1 over s plus 1 over s squared plus 4. Nobody asked me for capital Y. I want little y. So I take the inverse Laplace transform of both sides. Inverse Laplace transform of capital Y is little y. Inverse Laplace transform of 1 over s is 1. Inverse transform of 1 over s squared plus 4 is sine of 2x. That's the same answer we got solving this using conventional methods, solving this as a non-homogeneous linear second order DE. Okay, so sorry for all that confusion in the middle. In fact, I'm probably going to put in the notes, skip a bunch of stuff. So hopefully you skipped over until this made sense. I'll make a video nice and clean where I do another example.